So for this particular state table, I have present states, input, next state, and the output. So for this, with the help of present state and the input, you are going to find out the next state and the output. Okay, so the present states are AB, for which the input is X. The next state is going to be A n plus 1, B n plus 1, output is Y. Now for these present states, that is nothing but the representation of the states S0. So for S0, if the S0 is 0 0, so for state S0, the input may be 0 or it may be 1. So there will be two combinations for which the next states, according to the state diagram, S0 goes to S0, that is nothing but the next state is also S0. S0 goes to S1 when input is 1, so it is 0 1, and both the cases outputs are 0. For S1 state, that is 0 1, input can be 0, can be 1. It is going to S0, output is 0, and it is going S2, for output is 0. Next state 1 0 1 0, that is nothing but a S2 states. So S2 state, for x is equal to 0, it goes to S0, output is 0, and it for x is equal to 1, it goes to S3 state and the output is 0. And finally for 1 1, when input is 0, it goes to S0, output is 1, the sequence is detected, 3 ones are detected, and if still the next input is x 1, so it will remain in the S3 states itself and the output is 1, and in this mode it is going to continuously detecting the sequence of 1 1 1s. So these are, first two are for S0, these are for S1, S2, S3. Okay, now what I left this column for, this column is for input to flip-flops. So this is nothing but through which flip-flop you are going to design the circuit. So input to flip-flops, so I am going to consider here two flip-flops since the number of tables are required, so excitation tables. So I will be getting here DA. Let us design this whole circuit or the state with the help of D flip-flop. So it is DA and DB are the output, and through the excitation table of D flip-flop, it is clear that the next state is delayed. Means what? DA is as it is what is at the next state. So this next state column I will be copying up here. So this will be 0 0 0 1, afterwards again 0 0 1 0. Okay, that's all about the D flip-flop and the state table. After solving the K-maps for the output Y, DA, DB, okay, what equations we got here? For DA, it is AX plus BX, that is nothing but I can modify it to taking X common and A or with B. The second way, DB, the equation for DB is AX plus B bar X, and once again DB can be modified to taking X common, A or with B bar, and finally the output Y. This is the K map. It is clear that it is common for these two cases, for which AB is common, X is variable, so it is AB. So these are the three equations we need to implement, DA, DB and Y, through which we will be able to calculate the sequence detector. So let me draw the diagram. Flip-flop A, flip-flop B. Okay, synchronous flip-flop is there, so clock is common to both. So here is the clock given to both of the flip-flops. The input DA, DB, here it is QA, QB, QA bar, QB bar. Okay, flip-flop A is equal to X plus A or with B, that is nothing but QA or with QB. So we have two AND gates requiring two AND gates here, one OR gate to which one of the input is X, this one is A, B. Okay, so AX I am getting here. For DB I'll be requiring B bar X. Okay, so this is the AND gate, one more AX. Okay, so that's all about the circuit diagram. Y is remaining here, so output Y is nothing but the product of A and B, so that is nothing but Y is equal to A into B. So that's all about the logic diagram for the sequence detector. Okay.